Welcome to the Deep Dive. We're the show that tries to cut through the noise and get straight to what really matters in tech. And today we are driving headfirst into something huge. This relentless, almost insatiable demand for speed and computing. You see it everywhere, right? AI algorithms, massive machine learning workloads, these gigantic data centers popping up constantly. Everything needs to go faster. But here's the real kicker, the paradox. How do you keep doubling data rates without everything just, sucking down insane amounts of power or becoming totally unstable? And that's exactly where our deep dive is focused today. PCIe 6.0, it's the latest step, the next evolution in these high-speed connections, and it promises this really staggering leap in performance. But well, as you can probably guess, getting that kind of speed brings some serious engineering challenges, especially around power consumption and keeping that signal rock solid.
Absolutely. And that's why this new standard, it wasn't just like an incremental upgrade. It really demanded a fundamental architectural shift. And that shift is centered around one core innovation, something called the L0P power state. So this deep dive, it's all about unpacking why L0P was absolutely necessary, how it actually works its magic, and the really profound impact it has on system-level energy efficiency.
Okay, so we got the stage set, the need for speed, the power problems with next-gen tech, and this hint that L0P is somehow the key. All right, let's pull back the curtain then. Let's really get into this revolutionary new power state and understand how it's changing the game for high-performance computing. When I first saw the numbers for PCIe 6.0 doubling the rate to 64 gigatransfers per second per lane, that's 128 gigabytes per second in a standard by 16 slot. My first thought was just, how? How did they manage that without just smashing into a wall of physics? What was the breakthrough?
Yeah, you're hitting the nail on the head there. That was the core problem. The old way of sending signals, NRZ, non-return to zero, just wasn't going to cut it. Doubling the data rate with NRZ, that would mean doubling the Nyquist frequency. Think of that as like the signal speed limit up to 32 megahertz. And at that speed, the channel losses, how much signal you lose over the wire, just become prohibitive. We're talking estimates over 60 decibels. That's just unmanageable with typical system materials.
60 dB. Wow. Okay, so NRZ was a non-starter.
Pretty much.
Yeah.
So the big decision was to switch to PAM4. That's 4-level pulse-amplitude modulation. Now, PAM4 is actually quite clever. It encodes 2 bits of data into one of 4 distinct voltage levels, all within a single clock cycle or unit interval. So you effectively double the data throughput, but you don't have to double that fundamental frequency. This lets PCIe 6.0 run at a 32 gigabo rate. That's 32 billion symbols flying down the wire every second, but at a lower, more manageable 16 gigahertz Nyquist frequency. And that keeps the channel loss budget much more similar to PCIe 5.0. Around 32 dB a break, which is achievable.
Okay, so PAM4 gets us the speed without frying the physics. But you mentioned trade-offs earlier.
Right. Here's the catch. PAM4 is inherently more power hungry. And crucially, it's way more susceptible to noise. Think about it. You're squeezing 4 voltage levels into the same space where you previously had 2. So the gap between each level, the vertical eye opening, shrinks down to about a third of what you had with NRZ.
So it's much easier to misread a 10 as a 11 if there's any noise or jitter.
Exactly. It's like trying to read really small print on a shaky piece of paper.
Yeah.
The margin for error is way smaller. And this leads to a much higher native bit error rate, the BER. We're talking maybe 10 to the minus 6 errors per bit. Naturally.
10 to the minus 6,
Yeah.
compared to what previous generations targeted.
Compared to like 10 to the minus 12, orders of magnitude worse, natively.
Okay, wow.
So you've got higher power draw at the physical layer, the PHY,
Yeah.
and this much higher error rate. That combo created this urgent need for, much smarter power management and some serious error correction.
So PAM4 was the speed enabler, but it came with this built-in headache of errors and power draw. Was it really the only game in town, or were other options seriously looked at?
Other things were considered, but PAM4 really hit the sweet spot for balancing speed gains against implementation complexity for this generation. The trade-offs were seen as manageable with the right architectural changes.
Which brings us to that error rate. If it's naturally so much higher, how on earth do you make sure the data getting through is actually correct? What had to change architecturally to handle that?
Right. That high native BER made hitting the traditional low error targets impossible without help. So that immediately forced another crucial shift, FOB mode. Slow T stands for Flow Control Unit. To handle all those errors, a lightweight forward error correction FEC mechanism became absolutely mandatory, and FEC algorithms, just by how they work, they need fixed-size chunks of data to operate on.
Okay. So the old way of sending variable-sized packets just wouldn't work with FEC.
Correct. Couldn't do it. So PCIe 6.0 had to fundamentally restructure how data moves. Everything gets organized into these fixed-size 256-byte FLITs before transmission.
Yeah.
Each FLIT has like 232 bytes for your actual data payload, 8 bytes for a CRC check that's error detection, and then 6 bytes for the FEC data itself, which allows for error correction.
Got it. Fixed blocks for the error math.
Exactly. But FLIT mode actually brought other benefits, too. It got rid of the overhead from the old 128B, 130B encoding.
Oh, yeah, where they added extra bits just for protocol stuff.
Right, about 1.5% overhead.
Yeah.
FLIT mode moves to a super efficient 1B1B encoding. No wasted bandwidth there. And, crucially, this fixed, predictable FLIT structure. It created the stable framework needed for new protocol tricks. Like L0P. L0P is only available when you're running in FLIT mode.
That's a huge shift, moving to fixed blocks. It obviously enables FEC and L0P, which sound critical. But does that rigidity cause any new problems? Like maybe it's less efficient for really small data packets compared to the old flexible way.
That's a fair point. There are always trade-offs in engineering. For very small latency-sensitive packets, there might be some padding needed to fill a FLIT, which adds a tiny bit of overhead in those specific cases. But for the high-throughput workloads, PCIe 6.0 targets, the benefits of FEC, and the efficiency of 1B1B encoding, plus enabling L0P, far outweigh that potential minor inefficiency.
Okay, that makes sense. So compare this new FLIT-based world to how power management used to work in PCIe. You mentioned it was more static.
Yeah, exactly. In older PCIe generations, power management was really focused on periods when the link was idle. You had states like L0s, L1, L2, basically ways to power down parts of the link when no data was flowing.
Yeah.
People had tried to do dynamic link width changes while data was flowing, but those attempts were really disruptive.
Disruptive how?
They effectively stalled all data traffic. The link had to basically stop, renegotiate the width, retrain. We're talking tens of microseconds of dead time. In high-performance computing, that's an eternity. Totally unacceptable for many applications.
Gotcha. So let me see if I'm tracing this right. It feels like a chain reaction. PAM4 gave the speed, but created the power and error problems. That forced the move to FLIT mode to handle the errors with FEC. And that, in turn, unlocked the possibility of doing something smarter about power during active operation, which became L0P. Is that about right?
That's a perfect summary. PM4 created the problem, FLIT mode created the opportunity, and L0P is the solution. It's this new power state that can adjust power consumption while the link is active without stopping everything. And this is where it gets really interesting, because L0P is what fundamentally balances that power versus performance equation for PCIe 6.0.
Okay, great context. Now let's really zoom in on L0P itself.
Yeah.
What exactly is the state, and how does it pull off this magic trick managing power dynamically while data is still flowing?
Right, so L0P is technically a substate of L0. And L0 is the main fully active operational state of the PCIe link. Data's moving, everything's working. L0P's core job is dynamic scaling of the active link width. So imagine you have a wide by 16 link, 16 lanes. If you don't need all that bandwidth right now, L0P lets that link narrow down. You can go to by 8, by 4, by 2, even just a single by 1 lane.
To save power when you don't need the full fire hose.
Exactly. But here's the key innovation. This narrowing and widening happens without interrupting the flow of data. At least one lane always stays active, carrying traffic. So the whole process is seamless, completely transparent to the software layers above. They don't even know what's happening.
That is the magic trick. Okay,
Yeah.
How do the two devices on either end of the link coordinate this lane switching dance without dropping any data? What's this handshake protocol you mentioned?
It's a very precise, tightly timed handshake managed at the data link layer. That's layer 2 in the stack. Think of it like a very fast, synchronized conversation. Either device on the link can kick things off. Say an SSD just finished a big read and traffic drops. It can send a request to narrow the link. This request goes out either as a special packet called a link management DLLP data link layer packet, or it can be encoded into these things called ordered sets, which are special patterns sent between data.
Okay, so one side says, hey, let's use fewer lanes. What happens then?
The partner device has to respond. It sends back either an ACK, acknowledgement meaning okay, or an NK, negative acknowledgement meaning no, not right now. And that response has to come back fast, within just 1 microsecond in the high-speed modes or 4 microseconds at older speeds. Really tight timing.
1 microsecond. Okay. What if both sides try to change the width at the exact same time?
Good question. There's an arbitration mechanism. If both send a request simultaneously, there are rules. Usually the request asking for the narrower width wins, or sometimes one device might have higher priority. It's all defined to avoid confusion.
Makes sense. So that's the logical handshake. What's happening down at the physical layer, the electrical level, when lanes are actually switched off or turned back on? That sounds tricky.
It is. And importantly, all width changes in L0P has to be symmetric. If you narrow down the transmit lanes, you have to narrow down the receive lanes by the same amount. Keeps things simpler.
Okay, symmetric scaling. So how does downscaling work? Turning lanes off.
Once the handshake is done and agreed upon, the process gets synchronized to a specific point in the data stream, something called an SKP ordered set boundary. Then a special controlled SKP ordered set goes out, basically signaling, okay, we're changing width now. The lanes that are being deactivated send one final signal, an electrical idle ordered set, or EIS, and then they basically just go quiet. They enter an electrical idle state.
Meaning they power down their transmitters?
Largely, yes. The PHY circuitry for those lanes gets powered down quite significantly. The power savings are expected to be pretty close to a lane that's fully powered off in, say, an L1 state.
And the other lanes, the ones staying active?
They just keep trucking. Data transmission continues completely uninterrupted on the remaining active lanes.
Okay, that sounds relatively straightforward. What about going the other way? Upscaling, turning lanes back on? That sounds harder.
It is. It's definitely more intricate. So the lanes that need to reactivate, they first exit that electrical idle state by sending an EIOS, electrical idle exit ordered set. Then, and this is the really clever part, a kind of mini-link training sequence happens, but only on those lanes that are waking up.
Mini training, like the full training when a link first powers up.
Sort of, but much faster and localized. They exchange specific training sets, TS1 and TS2, just like in initial training. This lets them achieve bit lock, symbol lock, and tune their receivers the equalization process. But, and here's the absolute key, while this mini training is happening only on the reactivating lanes, the lanes that were already active, they're still carrying live data traffic the whole time.
Ah, so the main data flow never stops.
Exactly. Once those reactivating lanes are trained and ready, they send a special indicator called start of data stream, SDS, followed by one last control SKP set. And boom, the data stream immediately expands to use the new wider link.
Wow. That isolated training is really the core of making L0P non-disruptive then.
Precisely. It avoids that whole link halting recovery process that plagued older methods. It's a very complex piece of engineering, coordinating active data and training simultaneously.
Yeah, I can imagine. Does implementing something that complex bring its own set of challenges?
Oh, absolutely. We can definitely get into those. But it's also worth quickly noting the constraints on L0P.
Right. What are the rules?
One, it's exclusive to L-FLIT mode, so PCIe 6.0 and newer only. You won't find it on older specs. Two, it directly replaces the old L0 state. L0s is actually disallowed in LALOT mode because L0P does the job better for active power management. And three, both devices, both link partners, have to support L0P and agree to use it. It requires mutual support. One side can't just force it.
Okay, got it. FLIT mode only replaces L0s. Both sides need to agree. Makes sense. So we've gone through the why and the how. Now the big question, the so what. Why should you, listening right now, care about all this deep engineering? What's the actual real-world impact on performance and power in the systems you use?
Well, the absolute core value is that L0P makes power consumption directly proportional to the actual bandwidth being used at any given moment. An idle lane sitting in L0P. It consumes power very similar to a lane that's completely powered down. Now, for a big, wide by 16 link running at full PCI 6.0 speed, the estimates for power savings are in the range of several picojoules per bit.
Picojoule per bit. Okay, translate that for us. Is that a lot?
It's huge when you scale it up. Think about a data center filled with thousands of servers, each with multiple PCIe links running constantly. Several picojoules per bit, multiplied by billions or trillions of bits per second, across thousands of links. It adds up to massive energy savings.
Okay, yeah.
This has a direct impact on the total cost of ownership, the TCO, for data centers. Lower power bills, less heat to dissipate, which means lower cooling costs. It's a big economic driver. But what's really fascinating, I think, is how it lets individual components operate at their optimal power level in real time, constantly adapting to the actual workload demand.
That adaptability sounds key. Can you give us some concrete examples? What kinds of applications really benefit the most from this dynamic scaling?
Oh, yeah, absolutely. The poster child is probably AI and machine learning accelerators, GPUs, TPUs, things like that.
Yeah.
Their workloads are famously bursty or non-uniform, right?
Yeah.
You have phases where they're doing intense calculations on the chip and the connection back to the host CPU or memory isn't super busy. Then suddenly they need to load a massive new data set or model weights, and they need all the bandwidth they can get right now.
Right, that feast or famine pattern.
Exactly. L0P is perfect for that. The accelerator's PCIe link can dynamically scale down to, say, by 4 or even by 2 lanes during those compute-heavy phases, saving significant power. Then when it needs to load data, boom, it seamlessly scales right back up to the full by 16 width without any performance hit, without any delay. This dramatically improves the overall energy efficiency, the performance per watt, which is a critical metric for these huge AI training clusters.
Makes perfect sense for AML. What other areas?
Another huge one is data center networking and storage. Think about modern data centers moving towards these disaggregated or composable architectures.
Where resources like storage and accelerators aren't tied to one server.
Exactly. You pool resources, and I/O workloads become much more dynamic. L0P lets things like high-speed network interface cards, NICs, or NVMe SSDs reduce their link power when I/O demand is low. This is really crucial for supporting things like next-gen 800 gigabit Ethernet. You need the full PCIe 6.0 by 16 bandwidth to feed that beast without bottlenecks. But you're not going to be saturating 800 gigs constantly. L0P lets you save power during the quieter times.
Okay, those are great examples. Now, thinking about all these benefits, the power savings, the adaptability, what would you say is the single most significant performance advantage that L0P really brings?
Hands down, it's the non-disruptive nature. That's the game changer. Remember those multi-microsecond stalls we talked about with older attempts at dynamic width changes? L0P completely eliminates those. Now think about latency-sensitive applications.
Yeah.
Real-time AI inferencing, not just training. High-frequency financial trading.
Yeah.
Interactive cloud gaming.
Yeah, applications where even tiny delays or jitter can be disastrous.
Exactly. For those apps, unpredictable latency spikes are completely unacceptable. Those old disruptive methods. They'd make dynamic power saving simply unusable. L0P, by being seamless and non-disruptive, makes active power management a truly viable, even attractive option in these super performance critical environments for the very first time.
It's almost like the hardware itself is doing a kind of power virtualization, managing the resource transparently underneath everything else.
That's a fantastic analogy. I like that. Power virtualization at the hardware level.
Yeah.
L0P effectively decouples the logical bandwidth need of the application from the fixed physical number of lanes on the connector. A physical by 16 link can now behave like a dynamically resizable pipe. And it's all managed transparently by the hardware, no OS intervention, no driver fiddling needed. That is a real paradigm shift. We're moving from statically provisioning bandwidth to dynamically allocating it based on real-time need. That enables much more efficient resource utilization, especially in cloud environments where workloads are constantly shifting.
Okay, the concept sounds incredibly powerful, but has this actually been proven? Has anyone shown this working in practice, not just on paper?
Yeah, absolutely. While we're still seeing the first wave of widespread silicon adoption, there have been key demonstrations. Rambus, for instance, did a technical showcase using a Xilinx FPGA, a programmable chip. They showed a PCIe 6.0 link running, and it seamlessly transitioned from a by 4 width down to by 1, presumably to save power, and then scaled back up to by 4 again. And the crucial part, there was zero interruption to the data transmission visible at the protocol level. The data just kept flowing.
So a real-world proof of concept.
Exactly. It directly validated that core promise of L0P dynamic scaling without disruption, really highlighting the difference compared to older methods that would have caused that noticeable stall.
Okay, this all sounds genuinely revolutionary, pushing boundaries. But, anything this advanced, this complex, it must come with its own set of headaches for the engineers building it, right? It sounds like getting L0P designed and verified is, I don't know, like playing 4D chess with electrons, trying to keep everything perfectly synchronized. What's the trickiest part? Any war stories from the validation labs?
Oh, you are absolutely right. Implementing and verifying L0P is definitely not trivial. It presents some significant challenges. First off, there's just the sheer protocol and logic complexity. L0P involves one of the most intricate state machines in the entire PCIe specification.
Right.
You've got these complex handshakes, those really strict microsecond timing requirements for the ACKs and NAKs, and then this incredibly sophisticated logic to manage lanes that are actively carrying data in parallel with lanes that are going through that many training sequence during upscaling.
Yeah, coordinating active traffic and training simultaneously sounds like a nightmare.
It's a very, very tightly choreographed dance. And because it's so complex, pre-silicon validation becomes absolutely indispensable. You cannot wait until you have chips back to find problems. Early verification efforts, using advanced simulation and formal verification techniques, have already uncovered subtle but potentially catastrophic bugs.
Like what kind of bugs?
Things like deadlocks, where the two devices get stuck waiting for each other due to simultaneous requests handled incorrectly. Or incorrect sequencing of control signals during that lane reactivation phase, which could corrupt data or crash the link.
Ouch. So meticulous verification is key.
Absolutely critical. You need exhaustive simulation and formal methods that can mathematically prove the logic works under all possible conditions.
What about the physical side, the analog stuff?
Good point. There are analog and signal integrity concerns too. You're rapidly turning power on and off to fairly power-hungry PHY circuits on some lanes, right next to lanes that are actively trying to transmit high-speed data. That switching can introduce electrical noise or cause transient voltage dips on the power delivery network, the PDN.
And that noise could mess up the signals on the active lanes.
Potentially, yes. It could degrade the signal integrity, increasing the error rate on the lanes that are supposed to be working perfectly. So it requires really careful analog design, robust power delivery on the board and chip, and good isolation between lanes. Like trying to have a clear phone call right next to someone turning a noisy appliance on and off.
Okay, so complex logic, intense verification, tricky analog design. Anything else?
And finally, just ensuring smooth backward compatibility. The L0P logic in a new device has to gracefully recognize when it's talking to an older device that doesn't support L0P and make sure it never even tries to initiate an L0P transition with an incompatible partner.
Right. Can't break the old stuff. Okay, so a tough engineering challenge, but clearly the benefits were deemed worth it. Building on all that, what does L0P tell us about the future? Where do high-speed interconnects go from here?
Well, I think L0P's core principles, dynamic, non-disruptive power scaling, are likely to become foundational going forward. We're already looking at PCIe 7.0, which aims to double the data rate again to 128 GTs per lane. And one of its explicitly stated primary goals is improved power efficiency.
So L0P, or something very much like it, is probably sticking around.
Almost certainly. Dynamic scaling like this is becoming a baseline requirement for efficiency at these speeds. It's not just a nice-to-have anymore. And interestingly, this isn't the first time we've seen something like this. Intel's older QuickPath Interconnect, QPI, also had a state conceptually similar to L0P for dynamic width scaling years ago. It suggests this is sort of a natural engineering solution when you have high-speed multi-lane lengths. Convergent evolution, if you will.
Interesting. So where does it evolve next? What's beyond just reactive scaling?
The next logical step, I think, could be deeper system integration. Imagine a future where the operating system scheduler, or maybe a hypervisor in a virtualized environment, could actually provide proactive hints to the PCIe hardware.
Hints about what?
About upcoming workload changes. Like, hey, I'm about to start a massive data transfer in 50 microseconds. Or, this VM is going mostly idle. The PCIe link could then use that information for predictive power management, adjusting its width in anticipation of the change, rather than just reacting after the fact, moving beyond purely reactive control.
Wow, the system literally anticipating your needs down to the interconnect level.
Exactly. And stepping back even further, L0P really successfully extends that whole philosophy of energy proportional computing, where power use scales directly with useful work right into the high-performance I/O subsystem. We've seen it for years with CPUs dynamically adjusting frequency and voltage, DVFS. L0P brings that same intelligence to the interconnect. So you can think of L0P as kind of a blueprint for future smart interconnects.
Smart interconnects. What does that future look like?
We can sort of envision this intelligent adaptive fabric, a network within the system that dynamically reconfigures not just its bandwidth, but maybe even its topology and its power profile, all in microseconds, based on the real-time demands of applications. People are already talking about possibilities like asymmetric link widths for future standards, maybe more lanes transmitting than receiving, or vice versa, if the workload needs it. And PCIe over optical fibers is being seriously developed for PCIe 7.0 and beyond to handle longer distances and potentially even higher speeds. L0P feels like the first major concrete step on this path toward a truly adaptive interconnect fabric.
Okay, so let's try and wrap this all up. It seems clear L0P isn't just some minor tweak in PCI 6.0. It really feels like a cornerstone architectural innovation, a direct and, you argue, necessary response to the big challenges, power, errors, signal integrity brought on by PAM4 signaling, and just the sheer demands of modern computing.
Absolutely. And its key contribution is filling that critical gap. Managing power effectively during active operation. That's totally different from the legacy power states that only dealt with idleness. And that ability to dynamically scale without disruption, That is truly transformative for these bursty, data-hungry workloads like AI and machine learning. It lets systems be incredibly powerful when needed, but also intelligently efficient the rest of the time.
So bringing this home for everyone listening, for you trying to stay on top of where tech is heading, what's the biggest takeaway here? What should you really remember about L0P?
Maybe think about it this way. L0P moves us significantly closer to a future where your computer's performance isn't just measured in raw gigahertz or gigabytes per second, but in its intelligent adaptive efficiency. What if every single component in your system, from the CPU to the network card to the SSD, could seamlessly and transparently adapt its power consumption, second by second, microsecond by microsecond, to the exact demands of the work you're doing right now, instead of just running flat out or shutting down completely? How might that fundamentally change how we design systems, how we use them, how we even perceive what high-performance computing means in the years to come? That's the trajectory L0P puts us on.